Hello everyone, and welcome to our third and last lesson on kinematics. As promised, today we're focusing on proving and applying the 5 kinematic equations we discovered in the last video. As always, let me first present the goals we have for this session. After this video, we will be able to derive the kinematic equations, use the right kinematic equations in various types of problems, and interpret the results obtained in a problem. Now, recall the kinematic equations and, more importantly, under what conditions we can use them without any changes, as I will explain later. You probably remember that they apply to one-dimensional uniformly accelerated motions, meaning motions along only one direction and with constant acceleration. Now, let's start proving. We'll start by writing out the expression for the average speed, just as we usually do in mathematics. The average speed is then just the half sum of the initial speed, which we denote v subscript 0, and the final speed v. Although in our case, final doesn't necessarily mean the end of the motion. It is just the last moment we consider. Then, using this definition for average velocity and the physical definition, the rate of change of position or displacement over time, we have this new equation. We might want to explicitly write this difference or intervals. So we write displacement as a difference between the final and the initial positions. And while doing so, we also write the time interval in terms of the initial and final moments. Keep in mind that we can easily consider the initial moment to be 0. This doesn't affect our results because we only consider time intervals. But we'll continue the derivation, keeping t0 non-zero to make sure that this is indeed the case. Naturally, we might want to find the displacement or the position at a given moment in time. That means getting rid of the fraction. Then we get to write the following equation. Solving for x, the final position, we get yet another equation, the one under, in which we can replace the formula for the average speed or just use it as it is. However, we also note definition for the acceleration of a particle or a body, which is the change of velocity over the time interval, just as we have written on the slide. Like before, we explicitly write these changes, and the change in velocity will just be the final velocity v minus the initial velocity denoted v subscript 0. And the final moment t minus the initial moment t0 will just give us the time interval. We get rid of the fraction again by multiplying and obtaining an expression for the change in velocity. Solving for the final velocity, we get a very important equation that relates velocity and time. This is our third kinematic equation that we'll just write right after the first two. Going back to the position x and replacing the average velocity by its expression, we can further replace equation 3 into it. We obtain a rather long equation. However, this can be written in a prettier form by splitting it into distinct terms with position, velocity, and acceleration. Then we obtain the following equation, which is exactly the fourth kinematic equations we are looking for. Note that this relates position and time and acceleration. And now, this is equation 4. We put it on our list, and we are left with only one equation found by eliminating time in that last fourth equation. Express the time interval from equation 3, again with a fraction that comes directly from the definition of acceleration. We are free to plug it into equation 4. Now, the equation we obtain can be further simplified because the last two terms are similar. Using one single fraction and multiplying the first one by 2, so we have the same denominator, we can see that we can reduce some terms. In the end, we are left with a much simpler expression. This equation is usually written for the velocity v. In 2 easy steps, we obtain it in the exact form we want. Now that we know how to derive this fifth equation, the last one we were looking for, we realize that we derived all of them. Now that we know what lies behind these 5 equations, hopefully we'll feel more confident to use them. And let's try an example. One of the very important examples is applying them in the case of two-dimensional motion. We can do that because motions along perpendicular directions are independent of one another. This is always important in the case when we have an orthogonal system, as we have here, the system x or y, which has a 90-degree angle between the axes. In that case, we can just decompose the motion, meaning that we can consider independently the motion on the OX or horizontal axis and the OY or vertical axis. That happens because even if we have an acceleration on the OX axis, let's say, that won't influence the motion along the vertical axis. Then we can apply the kinematic equations independently on both axes, and that should give us both an easy and a complete description of the motion. The next slide is a drawing of such a two-dimensional motion. In the case where we have a negative acceleration on the y-axis, that is, in our case, the acceleration is towards the origin O throughout the motion, and let's say we have no acceleration on the x-axis. This is a very important real-life example. The quantities that we can measure and that we assume that we already know them and we can use them are the initial height h, which acts as an initial coordinate x0, the initial velocity v, and the associated angle that helps us decompose the velocity into two initial components. From that, we'll find that the initial velocity on the x-axis is v0x, which is v cosine alpha, and the initial velocity on the y-axis is v0y, which is just v sine alpha. We are particularly interested in finding the maximal height that the thrown body reaches, drawn h max on a drawing. The distance x or the distance d along the x-axis that the body goes along in the motion, and the final time tf that the body spends about the o-axis, which is a final time or flight time. For us to find these three quantities, we'll mostly use the last three kinematic equations because they are the most comprehensive and they are the only that contain momentarily physical quantities. So, as we said, let's split that motion into two parts: what happens on the vertical axis and what happens on the horizontal axis. On the vertical axis, we have the law of motion for the velocity, vyt being the momentarily velocity on the y-axis, and we see it's just the initial velocity minus the term given by the acceleration, because we consider that in our case acceleration would just be minus g, always negative. From that, as we said, we can particularize the equation for position, and using the fact that initially the body is at height h, we obtain the second equation, where the last term is exactly given by the acceleration. Then, if we want to get rid of time, we obtain the third equation, which relates the momentarily velocity and the momentarily position. The condition for the maximal height is just that velocity in that moment at that particular position will be zero because the body tends not to go any further, as that is the maximum height, but momentarily it also tends not to go back. Then we say that in that case Vy is 0, and in the third equation we see that we obtain that two quantities are equal. From that we find that the maximum height is, well, obviously greater than the initial height because our initial velocity was positive, and the difference is just the term v squared sine squared over 2g. Now we said we're also interested in the time of flight, and we'll consider that the motion stops when the body reaches the x-axis. When that happens, the y-coordinate will be 0, as is the case always for orthogonal coordinate systems. Then, if we plug this into the second equation and rearrange it to obtain a quadratic equation for t, we see that we obtain a rather complicated equation for t given by the quadratic formula, but this can be further particularized for, let's say, h equal to 0 or any other conditions we might be given in a problem. Now, we also wanted to find distance along the x-axis, so you must look into the horizontal motion as well. In this case, as we said, we have no acceleration on that direction, so the speed or velocity will remain constant, equal to the initial velocity, which is just v cosine alpha. Then the motion will be linear and will have the position linearly increase with time, v times t times cosine alpha. The condition for the distance d that the body goes along the x-axis is that when the motion halts or stops, which is at tf, we are at coordinate d on the x-axis. Plugging that into the equation, we see that d is just v times the final moment in time times cosine alpha. We can replace tf using that previous equation and obtain something similar for d. Note that this can be easy simplified if we consider that the body starts from the origin, so h will be 0, and we are left with a square under the square root. Using these two independent motions, and in this case only 3 out of the 5 kinematic equations, we see that we can completely describe that motion we consider, although it seems a lot more complicated than the one-dimensional case we've seen until now. The main takeaways from both this example and proving that the kinematics equation have exactly the form we predicted is that the kinematic equations are used for one-dimensional uniformly accelerated motion. That is usually because motions along perpendicular directions are always independent. That means that complex motion can be understood easier if you consider independent motion given by the orthogonal axis. This was the third and last lesson on kinematics, and I look forward to seeing you next time when we'll dive into dynamics and we'll talk about forces and Newton's law. Thank you for your attention.